It's okay. It's
All right, let's see. Sarah B. Claire. Matt. Luke. Jaden. Emma. Liza. Gotcha. Stuart. Ethan. Manya. Olivia. Kashal. Diego. Darwin. Sean. Yep. Jules. Doa. Yep. Matthew. Oh, okay, but he's coming back. All right, that's fine. Colin. Emily. Rennick. Yep. Sarah T. And McKenna. Okay. All right, is there anybody here whose name I didn't call? Name, please. Luke. Shoot. Let's see. Already. Oh, I got you. Okay. Can you remind me your name? Emily. Right. And McKenna? Okay, let's see. Looking for Claire, Matt, Kashal. Nope. Okay. Oh, time to get started. Okie dokie. So here's what we were talking about last time. We were talking about implicit differentiation, or more importantly, though, the implicit function theorem. So implicit differentiation is what you're allowed to do after you've established that one of the variables, for example, perhaps y here, can be locally viewed as a function, right? After you've established that, you can do implicit differentiation. How does one establish that it actually is a function? Well, aside from solving for it, which is, sometimes just not possible. The way you establish that it is locally a function is with the implicit function theorem. So we talked last time that you can argue as follows, roughly speaking, if you've got a problem, right, that problem is going to come in the form of the function being in the process of wrapping under itself. By the way, I'm leaving out all the formalities here. I want to give you all an intuitive point of view on what's going on with this theorem. So that's what a problem looks like. And then notice, well, yeah, but that would mean we have a vertical tangent line. And then that would mean that the gradient, keep in mind, I forgot to remove this. I forgot to remove the, let me just do that. There we go. It's all gone. The gradient of that function that I'm looking at a level set of would have to be horizontal. And of course, horizontal, I'm still in the wrong mode here. Horizontal would mean that the partial with respect to y is 0. Second component is 0. Okay, so the theorem, as is usually used then, is, the theorem as it usually is used is not like this, but rather as the contrapositive. And again, the contrapositive says if that doesn't happen, then that implies that that doesn't happen, which we write like so. Okay, so we talked about that last time. This is what I would call a rough cleanup of again, what in an ideal world would have been done in a single variable calculus class, but of course they can't. Okay, all right, but now let's take this same idea and apply it to the multivariable setting. And again, we did this last time, which is why I'm going quickly here. But that same idea, if you have a level set of a function of 3 variables, thus giving you a surface, right? In other words, if someone gives you an equation that involves 3 variables and you interpret it as a level set of a function, can I, for example, can I think of z as being a function of x and y, perhaps? You know, is that something that I can do? Am I allowed to talk about the partial derivative of z with respect to x, perhaps? Again, you can't just decide, hey, I think I'd like to do this. I think I'll go ahead and do it, right? You've got to establish that it is a function before you do something that only applies to functions. So how do I decide if z can be viewed as a function of x and y? Well, we need to make sure it's not currently in the process of wrapping under itself, such as at that point where we have a problem, right? Which would manifest by having a vertical tangent plane at that point, which would cause then a horizontal gradient again, which would mean that the partial with respect to z would be 0. So you see that there's really, I mean, if you take out sort of all the in between, problem means the partial with respect to that variable is 0. And so the contrapositive, if that doesn't happen, then we can conclude that there is no problem. Okay. And that is how we state the theorem. So this is taken right out of the book. The implicit function, this is the multivariable implicit function theorem. And so if you are looking at an equation involving n variables viewed as a level set, and if the partial with respect to one of those variables is non-zero, then you can view that locally as a function of the other variables. Okay. And the shorthand way of remembering, saying, what am I taking the partial of what with respect to what now? Always take the partial with respect to the variable that you want to view as a function. I think that's an easy little simple phrasing that helps out a lot. Okay. All right. I think that's where we ended last time. So let's put that into practice. We're going to look at this surface right here. That's a surface. What does that surface look like? Oh my gosh, I don't know. But I can fairly easily confirm that this point satisfies that equation, and therefore that's a point on this, whatever in the world that is, surface. And so here's the question I want to ask. Can I view x locally as a function? Well, the brute force way to do that would be to solve for x. Well, of course you can't. Right. What else am I going to do about this? Well, we can use the implicit function theorem. X is the variable that I want to view as a function. So I'm going to take the partial with respect to x, see what I get. And of course, a little bit of calculus, right? take the partial derivative. We're interested in what that is at the certain point that we're given, at that point, 1, 2, 3, in a neighborhood of 1, 2, 3, can it locally be viewed as a function? And so I plug in that value. And so these numbers go into there, and the relevant partial derivative is 4, otherwise known as not 0. So no problem. Yes, treat x as a function all you want. Locally, it is. Everybody good? Okay. All right. Now, there is a next step here. And the book doesn't talk about this. And I honestly feel like this is what's about to come is the confusing part. So I think it's weird that the book leaves this out. But anyway, okay, fine. So one of the variables can be viewed as a function. How do I take its derivatives? Again, I can't solve for it, so I can't just say, solve, take derivatives. We know derivatives. What's the tricky argument that we can use to compute the derivatives of our newly found implicit function? And is there a nice succinct sort of punchline? So here's the way I like to think about this. I've got f as a function of the variables x1 through xn. Okay. And within that function, suppose that one of these partial derivatives is non-zero, and that, of course, therefore, as a consequence of that, I can view, I can view xi as a function of the other variables. And now I'm going to represent this, viewing xi as a function of the other variables. I'm representing that as I've got a whole new sort of level of variables back here. And notice, of course, it's all the same variables except for obviously not xi, right? The one that I'm viewing a function of the others is not among the others, right? Is everybody good so far? Okay, so yeah, so f is a function of all these variables, and then this one is a function of all but, of course, itself. Okay. Right, so a reasonable question one could ask then, looking at this function, what is the, I'd like to be able to take derivatives of xi with respect to different things. What, for example, is the partial derivative of xi with respect to, let's say, xj? So what is this specific partial derivative there? Right, so does everybody see how this is the question we want to address here? This is, I had been viewing xi as being an input variable to the original f function. I'm now viewing it as a function on its own of the other variables. How do I take partials? By the way, let me also take this opportunity to point out, isn't it nice having this diagram here to keep track of what's where? I would absolutely get lost and confused, and I don't know how I'd keep it straight without having these diagrams. So I want to implore y'all, draw these diagrams as needed, right? I mean, if it's not just perfectly obvious to you what's a function of what, etc., you should give yourself a little roadmap. It's a safety measure, if nothing else, right? But really helpful in doing these kinds of calculations. Okay. So here's a next observation I should make. Again, looking at these variables as being, xi as a function of the others, and since we are taking a partial with respect to xj. Let's keep in mind what partial derivative means. Partial derivative means I'm going to vary that variable and all of the other variables are constants, right? So all of the other variables are constants. And let's remember where those other variables are. It's these variables. The xi is not one of these variables. It's not an input variable for this function that I'm taking a partial with respect to. So xi is not constant. But all these variables in here are constant. Now, xj is not constant because, again, that's what I'm taking a partial with respect to. But then all these variables down here, all constants. Everybody on board? And of course, I mean, let's not lose sight of the fact that really those are just recopies of these other variables here. So these are all constants. Okay, so you can see the things are starting to take shape here. And let's ask how I take then, just to kind of get the ball rolling, to have something to do. I'm going to take a derivative that I know the answer to. I'm going to take the derivative, excuse me, of f with respect to xj, and I claim that that's 0. And I'm going to claim that it's kind of obviously 0. It's 0 because, in fact, that's the whole point to saying that xi is a function of the other variables. When I here, let me do it like this. When I say that xi is a function of the other variables, what I mean is, as I change the other variables a little bit, there will always be some xi that I can put in here that makes this equation work. So in other words, xi as a function, its goal, its job, the thing that makes it exist is that it makes f not change. Right? So if f isn't changing, f is constant, right? Then, well, its derivative is, of course, 0. Is that good? All right. God, I don't know what I'd do about these kinds of questions if it weren't for the diagram. Very confusing otherwise. Okay, so yeah. So that partial derivative is 0. Yes?
Would you mind walking through the chain rule with delta f over delta xj?
You talking about this down here?
Yeah.
Oh, yeah, I haven't gotten to that yet.
Okay.
Oh, yeah, yeah, of course. Of course. That's my next thing. Yep. Any questions on what we've done so far? Yes.
The part where you said df or delta xj has to be 0. Just can you re-explain that?
Yeah. Well, so the idea is that this function, I forgot what color I used, but anyway, f is 0, right? So when we say that xi is a function of the other variables, what we mean is xi is defined to be whatever it is, nearby, locally, whatever it is that it has to be to make f remain constant. And if f is fixed, constant, not allowed to change it from 0, it's always 0, well, then its derivative is also 0. Yeah. Yep.
Is that the level set?
Yeah, absolutely. So in fact, that's, one way to think about this, one way to think about what we're doing when we were taking a partial derivative. Actually, let me come back up here to where there's an easier picture to deal with. When I look at a point like this and say that it's locally a function, one point of view that you could take is that I'm rewriting, in some sense, I'm reinterpreting this little bit of curve, which was previously viewed as a level set, and I'm reinterpreting it as a graph. Oh, I need a different color. As a graph where y is a function of x. So arguably, the implicit function theorem turns level sets into graphs. Yeah, totally. Okay, so that partial derivative is 0. Here's the thing, though. I also can compute this partial derivative, the composition partial derivative here, I can compute that with the chain rule. Right? And so here we go. Ultimately, the partial derivative I'm interested in, partial with respect to f with respect to xj. Well, there's 2 intermediate variables. I mean, in some sense, initially, let me do it like this, by the way. In some sense, initially, there's a bunch of intermediate variables. But the thing is, they're mostly constants, right? All of these paths that I'm talking about here, no changes can propagate through those paths. We're holding all those gray intermediate variables constant because we're taking a partial derivative. So I don't even have to worry about those. All I have to deal with is this path, because xi is in fact changing, right? And then this path, because xj, of course, is changing. And now, okay, sure, fine. But don't forget, furthermore, that this partial derivative that I just got through writing with the chain rule is, after all, 0. So what I've got then is that the green term plus the blue term is 0, and solve for what you're interested in. And by the way, it's easy to lose track. What was I interested in again? Right? Why am I doing all this? I'm doing all this because what I'm interested in is the partial of xi with respect to xj. I'm trying to find that one partial, which is right there. So you solve for it, and that's what the answer ends up being. Yes.
Wouldn't it just be 0 since delta f over delta xj is 0?
Well, so oh, I hear what you're saying. Okay, so great question. There's a tragedy in the notation. Let me get rid of all the color coding here. There's a real unfortunate fact of the notation, and that is we have to distinguish between that partial derivative, where f is just viewed as a function of, directly as a function of these variables, versus, which by the way is what this is, versus this derivative, which is a chain rule problem. And believe it or not, in my experience, people usually just leave these variables names confused. Which seems insane, right? But so it's a really unfortunate notation, but yeah, that's how people write it. If you want to fix this, the fix would be to rename these new variables over here with primes, right? And it's the partial with respect to xj prime, arguably, that's equal to 0. Right, but the immediate partial derivative of f with respect to just xj, that one right there, well, that's, I mean, who knows what that is, right? Because as this xj changes, when we're talking about the green partial here, the assumption is that all of these variables remain constant except for xj. At which point then it is no longer the case that I can just say, oh, xi will magically adjust to make f remain constant. It just doesn't. And so that partial derivative is not 0. Yeah, it's confusing and really unfortunate. But again, that's this is, the way people tend to write it is to just leave it confused and just kind of remember in their minds which one they're talking about. Very unfortunate.
So this is just kind of like a result of us having the same variables.
Yeah.
Times.
Okay. Yep. Right. Because that's right. Because we're thinking of xj in 2 roles. We're thinking of xj as one of the inputs to f. We're also thinking, because of the implicit function theorem, we're thinking of xj as one of the inputs to xi,
Okay.
which is one of the inputs to f.
Okay.
So yeah, it's this is a nasty little problem. And again, if you want to put the little primes on here like I did here, then that does make the confusion go away. But it's also extra notation, and again, for whatever it's worth, nobody does that. Well, I'll say it's very rare. It's relatively rare. Yes.
Why is f only listed as a function of xi and xj?
Well, okay, because let me lose again the mess. We are looking at the partial derivative of xi with respect to xj. And when you do that, that means that all of the other input variables other than xj, which is our stated variable, all the other variables are required to be constant. So these are constant, and therefore these are constant. Right, and then likewise these, and therefore these, and likewise these, and therefore these. Yeah. So confused. Can you imagine doing this without the diagram? It blows my mind. A lot of people do. Yes.
I'm trying to think about how the primes would affect the rest of the equation. Do they? Like, are there
Oh.
other new primes in the second set, like second part of each plus sign?
So it goes there and there and there.
Then which part am I solving for?
Well, we're solving for the partial.
Involving the sign and the sign.
Yeah, we want this partial, which is that factor right there.
Okay, thank you.
Yep. Yes.
I don't really understand why we say that function always equals a constant, because then we're looking at the level set again, and I thought if you say, okay,
Yeah.
equals 0.
Right. So let me come back up here to this picture here, right? And if I say, well, y is a function of x, right? On this little piece of curve, y is a function of x. The way y is a function of x is that y changes exactly how it has to keep f constant,
Yeah, exactly.
right? But if I say, look, forget about y being a function of x, f is a free function. F is a function of x and y. X and y can move around in whatever direction, and I could talk about what happens when, what happens to f when x moves that way, or what happens to f when y moves that way, right? I mean, these variables can do whatever. They are now independent variables. And f is definitely not constant. Like I see here, we're clearly leaving the level set, and here we're probably leaving the level set, although the picture kind of doesn't make that as good. It's more obvious, at a point like here, right? Where if you move in the x direction, yep, you're off the level set. F is not constant.
Sorry, I still don't understand.
So f is this is a function, right?
Yes, I
Functions
know.
are allowed to
I'm
change.
looking at the level set right now, that always equals a constant. But
Yes.
I thought we were transforming the level set into a function. So basically, we
Yes.
have, if we had f of x and y was, for example, x squared plus y. Then we have y equals negative x squared.
Okay.
That's the function we are looking at, right?
That's the eventual function after you've decided that you're going to hold f constant.
But like let's just assume we've already proven that this is a function, and we are now working with the derivative of this new function.
Okay.
I don't understand how we can say, okay, y equals negative x squared, and we are saying that y is always constant. I don't understand why.
I'm not saying y is always constant. So I'm saying that
say that the new function is constant, and therefore we can say that
well, f is constant. F is constant. So that's the one that I'm holding constant, and it is by holding that constant that I can say, as a result of that, I can therefore view this as being a function of the other variables. I think this is an office hours problem. So yeah, come on, we'll straighten this all out. No problem. Okay. So let me put a pin in that thought, and then just you can follow along the rest of the reasoning, and we'll straighten that out later. So punchline though, this all easy to solve for. We have these. Let's see. Let's see here. So that term comes from that path, and this term comes from that path. And of course, one of these partials is easy, right? That the partial of xj with respect to xj, that's obviously 1. Yeah, yes.
So if in the last term of the chain rule thing,
Uh-huh.
delta xj over delta xj, if we're effectively treating those as two different variables.
Yes,
right?
they're two different variables, but the definition of xj prime is that it is xj.
So, okay.
Yep.
I guess I'm just confused as to how we can treat them as different variables and it's still.
Yeah, well, I'm not saying they're independent variables. I'm saying they're different. This one here is an input to that function. This one here is not. That one there is an input to that function.
So then couldn't one of them change without the other changing?
I'm defining this variable to be that.
Okay.
Yeah. That's why that's why people want to just call it XJ in the first place. I mean, which again, a little sloppy, right? But the whole idea is that, well, yeah, but they're the same values.
Okay.
Yeah.
So like any other of the variables, like x1 prime could change, and that doesn't mean that x1 would, but xj.
No,
is
no, 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 no.
special.
These are the same. They're all, well, not X. There is no XI prime, of course, but all of these variables, they're all the same. They're all exactly the same.
Okay. I still, if they're all like defined as the same, then I still struggle with the delta f over delta xj being 0 in one instance and then not 0.
Let me ask you this question. If I were to say, I've got, y is some function of X, and then I'm going to introduce a new variable called T. And my definition of T is that X is equal to T.
Yeah,
That's cool, right?
yeah. But then, like,
But I could talk about, if I say Y is a function of X, X is a function of T, and technically we're doing the chain rule when I talk about dy dt versus dy dx. Those are different. One's a composition, one isn't. They happen to be the same value because X is T.
so in this instance, if we're saying like x equals t, then the derivative of y with respect to x and the derivative of y with respect to t should be the same, right?
In that instance, yes, because there's not other variables involved that I'm changing the rules for.
So that's,
But the thing is this variable is doing two different things. On the one hand, it's an independent variable for this function. It is also, I'm viewing it because of the implicit function. I'm choosing to view it in an entirely different capacity as being a function of these variables. So I think this is also an office hours problem. So let's just, put a pin in that and come talk to me in office hours. We'll get it all straightened out. Okay, so this is what we're interested in, right? This one is 1 because xj is xj, and this, partial of x with respect to x, right? It's always 1. And so we can solve for the one that we're interested in. The answer is that it's this formula here. And there you go. And the beautiful thing about this is this is now that we've made this argument, you can just use this result. Yes.
Why is it negative, like the term here, why is it negative? Should that be positive?
No. Why would it be positive? If you solve for this,
Because, yeah,
Right.
because like the last term is 0, so I basically just divide dx.
wait, what now? No. So this this comes over to the other side of the equation, right? Because we're solving for the green one.
If this one term is 1.
Yes.
Then any derivative of that equals 0.
No, I'm saying that this derivative is 1.
That's separate.
This is 1. The derivative itself is 1.
Okay.
Is that cool? Okay. Yeah. Okay. So pat formula, and you can just remember this formula and use it as needed. And there is bad news, good news. Bad news is that you probably won't be looking at a question where the variables are called x1, x2, x3, etc., and you're taking specifically the partial of xi, specifically with respect to xj. The variables are going to have all different names. Right. The good news about that is that there's a super convenient memory tool for remembering. Like, wait a second. Oh, I'm taking a partial of x with respect to z. So which one of these is my xi and which one is my xj? Super easy memory tool. The formula for what you're looking for, other than this minus sign, the formula looks like the little cancellation cheat, math crime that, we're all that we've talked about quite a bit, because it looks like, even though it doesn't, but it looks like these cancel, and then the xi goes up to the numerator, and, bam, right? It looks like it. And of course it doesn't. And of course that's a math crime, and that's absolute nonsense. You're not allowed to do that. But as a memory tool, it's great. Except for, again, this minus sign. And why is that minus sign there? Well, because it showed up in the algebra. We were solving for something in an equation, then had to subtract one term over to the other side. Right? You might say it differently as, why is this minus sign here? Roughly because this df and this df are not only not equal, I mean, they're not even, look, they're not even things, right? But if I were to pretend like these are things, you know, how much f changes as a result of this versus that, the whole point is that these are kind of opposites of each other, because they have to add up to 0, because f can't change. Right. So anyway, very important not to forget this minus sign. This minus sign is the sole distinction between the valid formula versus a, I don't know, maybe these DFs cancel. Right. So you take away that minus sign and it's wrong and highly suggestive of completely misunderstanding how the argument actually works. Right. So I emphasize the really important, don't forget that minus sign. It's a very, very big deal. From a grading point of view, if the minus sign's not there, it doesn't look like the student understands and just made a sign error. Right. It's really not just a sign error. It's a problem. So anyway, big deal. Okay. Last pause before we do an example. Yes.
So when is this to like bonded derivative of x with respect to another derivative without having to explicitly state that?
Yep, that's exactly it, right? That's exactly it. So you know, we have this theorem that says you can view this as a function, right? But I still can't solve for it. So exactly like you said, it is a function. I'm allowed to take derivatives of functions. I want to know the derivative of the function. How do we actually do that? Yeah, it saves you having to solve in the algebra, which again might be inconvenient, might be impossible. Right. Okay, so what we're going to do now is return to this example where we have a surface in which I can't solve for x, and let's see here. I'm looking near this point. I can view, you know, I've established that yes, I can view x locally as a function. So how would I take derivatives? What is dx? What is the partial of x with respect to z, for example? I mean, x is a function of y and z. So what's its partial derivative? And well, okay. Partial of x with respect to z. We write this down. Nice little shorthand, again, being first commit the math crime of pretending that these things cancel, which of course they don't. And then don't forget again, in order to for this to not be nonsense, you got to have that minus sign in there. Totally critical. So there's the formula. The various partials are easy to compute. Let's see, the z partial. Super easy, right? The x partial. In fact, we've already computed the x partial. I'll remind you, we computed the x partial as part of establishing that we could do this stuff in the first place, right? So you don't even have to recompute it. That's just a recopy. And then plug in the point you're interested in. Right near the point 1, 2, 3, you plug that in, and there's your answer. Okay, we good? Yes.
Can we just clarify what the meeting or like what the preliminary was in order to do this process? So
Yeah.
just that the derivative or the partial derivative does not equal 0 at the point, which means that the function doesn't wrap under.
Yeah. That's right. That's right. So the first thing, so if the question were kind of a combination of the two questions the two examples that we have here. You know, the first example says, is it a function? Second example says, what is that partial derivative? Right. Step one. And by the way, that's how questions tend to come at you. So thanks for the question. By the way, this was going to be the next thing I was going to talk about. If the question is, here's a surface and a point, what is the partial derivative? Step one is to establish that the thing you want to take the partial of is a function, right? So your first partial is going to be, this is going to be counterintuitive. You're going to take the partial first with respect to the thing you want to take the partial of to establish that it's a function, right? Okay, and then having done that, now you know X is a function. Now you know that everything that we do here is all reasonable, and therefore I can write down that formula. And then you're taking a partial next with respect to, let me zoom back in so we can see. Next, you'll take the partial with respect to Z to get your numerator.
initial part and equal to 0, we couldn't do this chain reaction.
Correct. Until we've done this, this is all wishful thinking, because I can't just declare that that's a function because I wish it was, and then start drawing arrows and talking about the chain rule, right? If that's not a function at all, then this whole thing crashes and burns and it doesn't make any sense at all.
Okay,
Yeah.
thank you.
Yep. Okay. All righty. Everybody good? Okay, so that finishes up chapter 2. We move on now to chapter 3, which is super short. We're not going to finish it today, but we'll probably finish it on Friday, be my best guess. So we'll be in chapter 5 next week. Oh yeah, so let me point out, since we're getting close to it, we're going to momentarily skip over chapter 4. If you take a look at the lecture schedule, you'll notice that that's reflected on the lecture schedule, that chapter 4 comes after chapter 7, at the very end of the course. And the reason for that is that chapters 6 and 7 are the hardest chapters in the book, I believe, for most students' experience. And so I want to get to 6 and 7 as soon as possible. And chapter 4 is the only material really in the course that isn't prerequisite to chapters 6 and 7. So chapter 4 being, in some sense, a side topic, we can put it anywhere we want. I'm going to do it last so we can get to those hard sections as soon as possible, so you'll have as much time as possible to absorb those ideas. And history, my experience is that this is helpful in teaching Math 212, which is, again, not that different from 219. Okay, so coming up soon. Chapter 3, parametric curves. Y'all know about parametric curves, right? So just going to kind of make an observation here. 3.1 is mostly the following relatively innocent observation, and that is that the derivative matrix for a parametric curve, well, there's only one output variable, one input variable, so therefore only one column. I mean, everything's a function of just t, right? So you get a single column matrix, and in fact, it's exactly the derivative of the parameterization. And derivatives are easy to write down as limits. That's the definition of a derivative, a single variable, derivative of a single variable function. And then we can geometrically start drawing pictures and try to figure out what this actually means. And this numerator is that difference between one point on the curve and then, some, h seconds later point on the curve. When you divide by h, right, well, then you're going to get something parallel to that. And then we take a limit as h goes to 0. Now, okay, so what does happen when h goes to 0? Well, a couple of things happen. As h gets closer and closer to 0, that vector gets shorter and shorter and shorter, right? The numerator gets shorter and shorter and shorter. The denominator, though, does too, right? The denominator is getting smaller and smaller and smaller. And so we're taking these vectors, these difference vectors that are increasingly, increasingly kind of closer and closer to being tangent. And we're looking at short distances along them and dividing by the short time differences. And in the limit, we're going to get something that's tangent to the curve and whose magnitude is the speed. Because, well, after all, we're talking about distance, right? So distance per unit time. Right? Distance per unit time is speed. So the big idea then is that, what the derivative matrix computes for is specifically a parametric curve. Well, it computes the velocity vector. A tangent vector whose magnitude is the speed. That's one of the first things we did is talk about velocity as such. Everybody good? All right, and then I'm going to say likewise, in the same sense that the derivative of position is velocity, the derivative of velocity is acceleration. And typically we represent velocity with v of t and acceleration with a of t. All vector valued. So that leads to questions kind of like this, where, suppose you're given velocity as a function of time and you have an initial position. By the way, sound familiar, right? You all seen questions like this in single variable calculus classes, or, velocity is just a single variable velocity, but still given a velocity, given an initial position, and you can compute from that various things. What is acceleration? Well, acceleration is the derivative of the velocity. No problem, take the derivative. What is position? Well, position is the antiderivative of velocity. Right, so antiderivative of velocity, antiderivative of that vector valued function. Hope it comes as no surprise. You take antiderivatives one term at a time, or one coordinate at a time, just like you take derivatives one coordinate at a time. So easy antiderivatives. Don't forget, of course, when you take antiderivatives, you get an integration constant. Right? How do we evaluate the integration constant? Well, let's see here. Can I squeeze all this onto the screen? Let's just, okay, I guess I'd better do it like this. So at t equals 0, we plug in t equals 0. Don't forget, of course, we know the position where x is when t equals 0. Then all of these are going to become 0. And then this equation turns into this equation, because position is 5, 6. This antiderivative that I'm looking at, again, you plug in t equals 0, you get 3, 1. And that allows me to solve for what I'm interested in, namely that constant c, that integration constant. Everybody good? Again, familiar? This is just kind of a vector version of something you've seen before in Calc 1. 1 or 2, depending. Okay. Now, I do want to point out one thing. A lot of students misunderstand and are under the impression from seeming experience that the constant, the integration, well, let me do it like this, that the integration constant will always be the same as the initial position. And that's not always true. In fact, it's usually not true. And tragically, the way a lot of examples in this area are done, it looks like it's usually true, even though, again, in real life, it's rarely true. And the reason why is real simple to follow. The reason why is most of these functions that are given to students are polynomials. And if this is a polynomial, then everything in here is going to be a polynomial, the antiderivative of a polynomial, which is always going to have, every term will then have a factor of t. And then when you plug in t equals 0, all of that goes away. You get a big fat 0 there. And so no surprise, in those cases, the integration constant will be the same as the initial value. But it's a pure consequence, 2 seconds. It's a pure consequence of the fact that the functions that very often they give you in high school classes tend to be polynomials. And you can see all it takes is for this function, the given velocity function, to just not be a polynomial. And then all of a sudden, well, there's lots of functions where you don't get zeros here. And if you don't get zeros there, then of course, why would those things be equal? Yes.
But you don't need like the point at t equals 0, correct? Like if you're given a point at say t equals 3.
Oh, correct. Oh, yeah. No, that's right. If the initial condition is some value, yeah. So choose this to be whatever it is that allows you to take advantage of that. Allows this to be something you can plug in. Yeah, totally. Yep. Absolutely. Okay. So, yeah, so that's really all there is to say about section 3.1. I will also point out, a lot of students conflate antiderivatives with integrals too much. This is one of the most commonly misunderstood things about single variable calculus, in my opinion. So if you want to hear more about how antiderivatives and integrals are different things, I do encourage you to watch. I have a half hour or so recording on my YouTube channel. It's again in the miscellaneous topics section, and I go on at length about my 3 top pet peeves. The 3 biggest misunderstandings about integrals amongst high school calculus students, and one of them is that difference. Give that a look if you're curious. In this case, the punchline that I want to point to is that when you're taking this integral here, it's not area under a curve. So in fact, if it was up to me, I wouldn't even call this an integral. To me, that's an antiderivative. Right, and the term improper integral is just tragic to me. Anyway, I'm getting onto my soapbox. So anyway, this is in no sense an area under anything. Okay, and I'm out of time. How about that? Okay, so we'll call it a day right there, and see y'all on Friday. Have a good Wednesday. Okay, let's see. So that's page 2. All right.